These are from released exams, so let's see. An amusement park ride consists of a rotating vertical cylinder with rough canvas walls. The floor is initially about halfway up the cylinder, as shown. After the rider has entered the cylinder, is rotating sufficiently fast, the floor is dropped down, yet the rider does not slide down. The rider has a mass of 50 kilograms. The radius is the radius of the cylinder, R, is 5 meters. The angular velocity of the cylinder when rotating is 1/3 rotations per second, and the coefficient of static friction between the rider and the wall is 0.55. All right. They've certainly given us everything we're going to need. This feels like an exercise. To me, an exercise doesn't really require you to do a whole lot. Just apply the rules and solve a problem. So on the diagram above, identify the forces on the rider when the system is rotating and the floor is dropped out. Well, I think we can come to this conclusion pretty quickly. Can we all agree there's going to be weight downwards? And the surface they're against is the wall, so normal force this way. And that means friction has to be upwards to prevent them from sliding downwards. Yeah? It is the normal force that is causing a centripetal acceleration. It's also causing friction. Calculate the unbalanced net force on the rider when the cylinder is rotating and state what provides the force. Normal force from the wall. I don't know if you get the answer correct unless you said from the wall. Do you understand what I mean by that? Normal force from the floor. No, it's the normal force. It's the wall that provides this force. So not really understanding the question, not knowing whether they want me to name the force or name the object that provides the force. I think you need to make sure that you answer the question thoroughly, and that's thoroughly. So I don't know if you just wrote normal force, if you would get full credit or not. I have to calculate it, though, and that means net force equals MAC. So I'm going to do M omega squared R, because they gave me omega. So I see no reason to use V squared over R. Omega is 1/3 rotations per second. And I know I can't use that here. I'm going to have to use radians per second. So I'll need to convert. And I know that one rotation is 2 pi radians. So cancel out the rotations, be left with radians, and I'll get 2 pi over 3 radians per second. So now this equals M, I don't know, how big was this guy? 50 kilograms. So 50 times 2 pi over 3 squared times 5. I don't have my calculator handy. It's over on my teaching desk. So I will have to use my phone, which is not good. I try to model the appropriate behavior, but it's just going to have to be this way. All right, 2.094 squared, 4.38 times 50 times 5. I got 1097 newtons. That has to be the unbalanced force that causes centripetal acceleration. Any questions? Alrighty. Calculate the required upward force that keeps the rider from falling when the floor is dropped down and state what provides that force. Friction. Now, it seems to me you only have part of an FRQ here. You see, I only gave part, because there's got to be another question, right? This isn't asking enough to me, especially if this is all you wanted to see. What do you think the other question was? Sorry?
The next question is the coefficient of static friction sufficient to keep the rider from sliding down the wall?
I think that'd be an excellent next question. Because we know the coefficient of static friction is 0.55. What we don't know is if is there enough friction. We need 500 newtons of frictional force to keep them from sliding down the wall because they have a mass of 50. So the required amount of static friction is 500 newtons. And I know that static friction is a inequality here, so I just need to make sure I have enough. And this is going to be 0.55 times 1097. Which gives me 603 newtons of available friction. I need 500. So I should be fine. Right? This problem doesn't have very much. Believe it or not, nowadays, this kind of spinny problem, they'd probably put it as just a multiple choice, or they'd have something else happen. That's it. That was the spinny ride problem. The skier starts from rest at time t equals 0 and is subject to a velocity-dependent drag force due to air resistance. And they give me a function for that. Force equals negative bv, where v is the velocity of the skier and b is some positive constant. I express all my answers in m, b, theta, and any fundamental constants. On the dot above, that represents the skier, draw a free body diagram indicating and labeling all forces that act on the skier while the skier descends the hill. I can only think of three. Normal force, weight, and drag. All good? All righty. Write a differential equation that can be used to solve for the velocity of the skier as a function of time. All right. Based on what I have there, this force will have to be broken up into two components, but we've kind of done this a few times. So mg sine theta and mg cosine theta. All right, so net force in the x direction equals ma. mg sine theta minus bv equals ma. And to make this a differential equation, I need to substitute a differential. I think the most appropriate one here would be any questions? Alrighty. Determine an expression for the terminal velocity of the skier. Terminal velocity of the skier is when it is no longer accelerating. So that is when mg sine theta equals bv. That is the terminal velocity. So the terminal velocity, mg sine theta divided by b. That's it. Now, getting an expression for v as a function of t, there's some work there. Not a whole lot, but there's some. But that's it. So unlike the way this was presented in 5th period, I'm going to present this as a straight ahead question in 6th period. And I want to do so by taking a look at situation A. In situation A, if there was no force from the fan, then it should be clear that there would be a frictional force this direction to hold the fan in place if this force didn't exist. All good? And still going to have, a gravitational force downwards, normal force perpendicular to the ramp. Those are still there. Now, us starting up the fan and adding an upwards force or a force up the ramp doesn't necessarily flip friction right away. It probably just reduces it. Right? Now, we don't really know how big the frictional force is. Perhaps frictional force on its own wasn't enough to keep the fan in place. But the fan pushing up the ramp could. Follow me so far? All right. So, let's consider the minimum. As FA gets smaller, this frictional force will have to get bigger in order to hold the fan in place. Now, unfortunately, we might have a threshold here. So we've done enough problems, I believe, that involve ramps where I think I can say net force in the x direction is going to be set equal to 0. We're still trying to make sure the fan stays in place. And I'm going to make down the ramp positive, which means mg sine theta minus the static friction and minus the force from the fan equals 0. Any questions? I also know that the net force in the y direction will equal 0, so normal is going to equal mg cosine theta. There's nothing else happening here. Don't think I have to spend a lot of time on that. All right. Friction is less than or equal to mu times the normal force. I think we are still best served subbing into your inequality. So that's what I'm going to do. Normal force is easy, but I do have to do some work here in order to have an expression. So let's do that. Static friction will equal mg sine theta minus Fa. All good? Any questions? All righty. So let's substitute into my static frictional force equation, and I'll get mg sine theta minus the applied force is less than or equal to mu s mg cosine theta. I need to figure out the size of the applied force, and I need to solve for the applied force. And I'll get that the applied force is greater than or equal to mg sine theta minus mu s mg cosine theta. And although somebody in 5th period asked, why did I flip the inequality? The truth is I didn't. I just added Fa to both sides, subtracted mu s mg cosine theta from both sides, but then wrote it with Fa on the left. Does that make sense? If not, do it your way. It's just algebra. But I get a minimum. It says that Fa has to be greater than or equal to, which means there is a minimum when it's equal to. It can be bigger than that, but the minimum will be when that's an equality. And that's kind of what I was shooting for. So if I want the minimum, it's what it equals, mg sine theta minus mu s mg cosine theta. It can be greater than that, but if I want the minimum, there's that. Now, question number 2, derive an expression for the maximum force. All right, that changes things. If dealing with the maximum, well, now we're beginning to push so hard on the fan that if there's no friction this way, it might start sliding up the ramp. That could happen too. Friction can act in either direction. It's trying to prevent one surface from sliding past the other. So we have just increased the size of the applied force so that this force switched directions. Still staying in place, I hope. But that does change things down here, doesn't it? That means I'm probably going to have to say something like net force in the x direction equals 0. But I don't think I have to start from scratch. The only thing that happened was this changed direction. So I'm going to keep everything else the same. I'm just going to make that positive. I'm going to reuse the work here. That should speed things up. I'm going to do the same thing. I'm going to solve this for the static frictional force. I'm going to substitute this in for friction in my inequality. Nothing has changed in the other direction. And now I'm going to solve for the applied force. This looks like a maximum now, right? I need to keep the force from the fan less than this amount. And the greatest it can be is when it's equal, so max is when this becomes an equal sign. And funny, that looks true. Like this number here will be less than this number here. In one case, I'm adding the two things together. In one case, I'm subtracting them. Seems to make perfect sense. Move on? Go ahead.
For part A,
Yeah?
would the free body diagram represent B1, or do we have multiple free body diagrams to play?
Nope. Free body diagram, you could have put the frictional force in any direction and you would have been okay. Because there is clearly not a right or wrong way. It can be in either direction. In fact, this bigger statement here is that in real life, if you work this problem out and you have decided a direction for the frictional force and something doesn't seem correct, it could have been that your situation has actually created a sense that the frictional force is working in the other direction. And look for it. You can see it. Here you can see what kind of changes it would make in your value or in your answer. All righty. Case B, the fan's being pushed down the ramp. Friction is going to be up the ramp, right? Because there's no chance that the fan direction is, there's no force to cause the fan to go up the ramp. So the only thing that could possibly hold it in place will be friction. I am not redoing all the work. It's just going to be mg sine theta plus the force from the fan minus friction. It's got to be equal to 0. There's no reason to redo the work. So static friction is equal to mg sine theta plus FB. Just doing the same problem a third time. Bless you. Bless you. So mg sine theta plus FB has to be less than or equal to mu s mg cosine theta. So FB less than or equal to mu s mg cosine theta minus mg sine theta. Yep.
Wouldn't it also be an equal sign because you're trying to find the force required to just get the box to start to move down? So
Yeah, I mean, truthfully, I should set that to make them equal, because that will be the amount to make it start moving. So, you're right. All right. Might as well answer question C. There is a coefficient of kinetic friction mu k between the friction block and the ramp. In case B, the box is given a gentle tap to break friction, and the block begins to slide down the ramp while the fan is still at the setting FB. Using your expression for part B, number 3, derive an expression for the acceleration of the cart down the ramp in terms of mu k, mu s, theta, m, and any fundamental constants. Wow. Down the ramp, up the ramp. Right? That's kinetic friction though. No more inequality. No reason to sub into an inequality either, right? It's a fixed value. It's constant. So I know they are equal. So I'll just sub in. By the number of you writing feverishly, this must not have been what you got. But FB can't be in our answer. But we have an expression for FB, right? So let's just use it. Be careful, 2 different mu's now. I know some of you are bothered by this, and neatness counts. Use the space you have. Take your time. Rewrite things carefully. Makes a big difference. I will point out that this term and this term cancel out. We determined the amount of force in FB in part from mg sine theta. We're looking at the differences between the 2 frictions. We determined how big the fan's force has to be by looking at the friction already. So we get mu s mg cosine theta minus mu k mg cosine theta equals ma. I do note that there is a m in every term. Do you see that? So we can factor it out and remove it. Now, there's no reason to do what I'm going to do next. You're done, technically. But I think it interesting that we get this here. It tells you a couple things, if you're paying attention. It tells you that, first, the acceleration is equal to something proportional to g cosine theta. Not surprising. If there's no friction at all, you would just get g cosine theta down the ramp. No, you get g sine theta down the ramp. So that's a little weird. So why is it so fixed with cosine? And I'll tell you, because it's friction that's determining what's happening here. That applied force from FB was determined by the friction. And then we subbed it in here. Now the interesting thing is this minus sign. Everything in those parentheses could be positive, negative, or 0 because there's a minus sign there. So if the static frictional force is greater than the kinetic friction, then tapping it will make it accelerate and get faster going down the ramp. Because when you tapped it, you broke the static friction, which was greater than the kinetic friction. So the friction is now suddenly less, and it will accelerate down the ramp. That makes sense. If The static friction and kinetic friction were the same, and I tapped it. All I did was give it velocity. But now that the friction didn't change, the net force was still 0 because that was the condition. So now it moves at a constant velocity with an acceleration of 0. And if for some strange reason you have a situation in which the static friction isn't as great as the kinetic friction, which is unusual, but I tap it, the frictional force will be greater under kinetic than static. The system will slow down and stop. That's what that tells you. You can read all of that from that statement alone. And it's all about that. That negative sign makes a massive difference. Pluses aren't particularly interesting. Negative signs produce the possibility of a 0. And therefore, they can be positive or negative. You always look carefully for stuff whenever there's a minus sign in your equation. Because that's where they ask those other questions, those leading questions, to try and get you to think about something. All right. Unfortunately, I didn't record any of that. But I recorded it for 5th period, so you just watch the one for 5th period. It's all the same stuff. We assume that based on the picture, I don't think the picture's great, but the arrow, that's pointing in the direction that the air's moving or the force on the fan is moving? I think that's the same thing, isn't it? So it seems to me like, well, no, they look opposite to me for some reason. So we're assuming that this represents the force on the fan and the direction of the force on the fan. It doesn't really matter because both cases are represented here, right? But since they're asking us specifically for case A, that's the direction of the force on the fan. Is that good for you guys? All right. So I'm going to start with a downward force for gravity. And based on the way that picture looks for A, there's an applied force along the ramp. There's a normal force this way. And I assume if the force up the ramp is big enough, this thing will slide up the ramp. So I'm pretty sure friction has to be acting this way. I think the other picture will be the same as that, except the applied force and friction will be reversed. So this makes a difference as to which problem you did. Any questions? Go ahead.
I didn't know there was like an applied force. I thought it was just friction
Okay.
applying on the fan.
A fan is attached to a friction block and set up so that it can apply a force to the cart as shown above. If that's not clear enough, I wrote parts of this. I took some of the pictures off of old AP exams and such, but I tend to have to rewrite questions from released exams sometimes to remove stuff that we haven't covered yet. Does that make sense? So I don't know if this is a sentence I wrote or not, but what I want to ask you is that not enough to tell you that there's a force applied to the block somehow?
No, it is.
Okay. So, and I don't mean this, I'm not trying to sound cruel. I want to make sure that tomorrow when you're taking your test, that's not these are going to be hard enough without misinterpreting the problem. And the misinterpretation, of course, makes it even harder. So as we look at this, some of you are, and I look at your work and I know the kind of people you are. You've got like stuff highlighted and circled and all that kind of stuff. You're going to town on editing the text there and parsing out the question. So definitely make sure you read the setup to the questions. There's going to be some stuff in there. And if you don't understand, when I'm in a room, you can just ask me, and I'll try and help you understand what's being described to you. But of course, we do have to move to a point where during the AP exam, you're on your own. Fair enough? All right. So good to go on? I'm doing case A. Not that it would matter. I just need to pick a case, and I asked apparently about case A. So I'm going to start by putting in a free, a coordinate system. I can choose any coordinate system I want because it's talking about just getting to the point where it's going to start to move. I'm going to assume that we're actually just before that. We're at the peak of the amount of static friction that can be offered in the problem, and we are not yet moving. Do you guys understand that reasonableness of that question? I mean, we're trying to figure out what's happening here. I think we have not broken friction yet and are staying in place. Can you guys even see those lines I just drew? They're so thin. There's probably an adjustment somewhere. I am not happy with this new piece of software. I even wrote a letter to the company. Well, I pay for it. I paid for the whole year in advance, like $65. So I'm like, I thought that would allow me to invite folks and have lots of screens out there. Nope, they disabled that. So yeah, I'm not happy with this company. I think the MG has to be broken up into its component forces. Don't you agree? So one of them this way, mg cos theta, and one this way, mg sine theta. That's pretty messy, but hey, you've come to expect messy from Mr. Shelton, I guess. All right, there we go. So everything I just did there, you would not be allowed to do on the test, right? Because I've changed the free body diagram. It no longer has forces on it. It has components of force on it. So if you have to do those things for your own, edification, don't do it in the box. Do it off to the side somewhere. Net force equals 0. So let's go ahead and start putting that together. I'm going to have mg sine theta plus friction minus the force from the fan equals 0. And looks like normal force minus mg cosine theta equals 0. Pretty standard stuff for an inclined plane. All right, this is not really stretching the whole inclined plane thing. And you've done inclined plane problems before, so this should have been pretty okay. But I see some people hastily writing down, which makes me very concerned, as this is just, part B. So derive an expression for the minimum force in case A required to get the block to start to move. So we're looking for F, the capital F there. I do know that static friction is less than or equal to mu times normal force. So to understand my max or min, I'm going to sub in there so I can get keep my inequality preserved, which means I'm going to solve this function for friction and this function for normal force. So when I do that, I'll get friction equals F minus mg sine theta. And this one, normal equals mg cosine theta. Any questions there? Yep.
For the mg sine theta, why is it not negative?
I chose down the ramp to be positive.
Oh, okay.
So, and both of those point in the same direction, so I made them both positive. Does that make sense? I mean, I could have made up the ramp positive, but I'd still have the same result.
Yeah.
But not a bad question. I'd love to say no questions are bad, but that's not true. We've seen it. So I'm going to basically sub in there, and same with this one. And I'm going to get F minus mg sine theta is less than or equal to mu s mg cosine theta. So F less than or equal to mu s mg cosine theta plus mg sine theta. That's what I get here. Any problems with that? Yeah.
So just because it asks for minimum doesn't mean
Well, no, I think I have a problem. Do you guys see the problem?
Yes.
I made an assumption at the very beginning, and I'm afraid I might have made the wrong one. If you don't see the problem, I really need you to pay attention now. This expression suggests that there is not a minimum. This says that my force can be any value up to some maximum value, right? That seems inconsistent with the question. And I think I made a mistake. I didn't think of the problem enough. Are you seeing the problem here? Because I know what I did. I made an assumption. And that assumption is that the fan was blowing strong enough that it was trying to push itself up the ramp. Right? And it says, derive an expression for the minimum force in case A required to get the box to start to move down the ramp in terms of theta, mu, m, and any fundamental constants. I think I made a fundamental flaw in the way I drew this. What's the flaw? Because none of you said anything about it, but it's plain as day. Go ahead.
It's not net force equals 0, it would be net force equals ma if it's moving down.
No, I still think the zero part's okay. I think the fundamental flaw is I set the problem up as if the block was going to slide up the ramp. Do you see why that is? What direction is friction? If the block was going to slide up the ramp, friction would be down the ramp, correct? I think when we set the problem up, we weren't carefully considering the possibility that the fan strength could have been so low that the frictional force was actually helping to keep this block from sliding down the ramp. Do you understand that? Because I drew the free body diagram just as it talked about. But that's a careful decision I should have made. I should have gone back and reevaluated my free body diagram. Right? Flipping that sign and changing the direction of friction makes this change, which makes this change, which makes this change. Now, I still have to solve for F. But if you're seeing the changes that are occurring, my F is still going to be a little different now. Now, is this more consistent with what they're asking? It gives me a minimum now, doesn't it? My force has to be at least this big or bigger to keep the fan from sliding down the ramp. Whatever that is. Go ahead.
Is the F next to the mg sine theta friction or force applied? Like in the
Force applied.
Did you mean to make it like multiplied? Like mg sine theta, is it minus or times f?
That's minus.
Okay.
Going at my handwriting today, got it?
Sorry.
Message received. Mr. Shelton, write neater. Got it. Yep.
So, since it says write in terms of capital M for mass, do we have to do that on the test?
You should, yeah.
Okay.
But as there's only one M here, it's not going to make any difference. If there were two M's and one was lowercase and one was capital, You should be very careful. Is it possible to go on? Now, you understand the very next thing is what we did first, right? Derive an expression for the maximum force in case A required to just get the box to start to move. I'm thinking I don't have to rework anything, do I? I at least don't have to do a whole lot, because in part 2, I'd have already done it in part 1. So I could just go back to what I had, where I had mg sine theta plus friction minus the applied force equals 0. My normal force will be the same, so friction is equal to Fa minus mg sine theta, and therefore Fa minus mg sine theta must be less than or equal to mu s mg cosine theta. And now I just solve that for Fa. So the problem asked for both. I just didn't conceive it right at the beginning. That was a problem on the exam last year when I gave this problem. A lot of students didn't read carefully enough and ended up having to redo both parts of the problem. They lost a lot of time. So the test I'm giving you tomorrow will have less interpretation like that, in the hopes that you'll still have enough time to complete the test. We still have more, but are there any questions about what's happening so far? All right. Derive an expression for the force FB in case B required to just get the box to start to move down the ramp in terms of theta, mu, m, and all the other stuff. I mean, this is a rehash of the same problem, isn't it? So I think on an actual AP exam, this would start to get redundant. I'm not sure there's worth doing this. If you can't do the top 2, you can't do this one either, right? And if you can do the top 2, you're just going to run out of time. So I think this is also a little long when it comes to your expectations for tomorrow's test. Everybody understand? This is probably too much time. I don't have to do a whole lot of new work, though. I mean, the applied force is now down the ramp, correct? And it's saying, drive an expression to just get the box to move down the ramp. So I am talking about friction being up the ramp. All good? So I'm looking at Fa plus mg sine theta minus friction equals 0. Still want to know where that threshold is. But I'm just looking at the picture. The applied force is down the ramp. Friction is up the ramp. And I'll have mg sine theta going down the ramp as well. Everything else stays the same. So I'm still doing all the same substitutions. So friction equals Fa plus mg sine theta. So I'll set that over here. And yes, I would expect you to be reusing stuff that you've already proven to save time. So that's all of that. Wow, a lot of work. That was 20 minutes of work. I'll have a coordinate system that's aligned with the horizontal and a coordinate system that's aligned with the vertical. All good? Excellent. So excited. This is theta. So net force in the x direction equals ma. And I think we're looking at F cosine theta equals ma. I think that's all I need to do, right? I don't need to worry about the y direction because I'm allowed to have theta, m, and f here. So A equals f cos theta over m. Oh no, I'm supposed to find f. What am I thinking? I should read my own question, I guess. So I guess it's ma over cosine theta. Yeah, a, m, and theta are in the answer. That looks like it. That one wasn't so tough. Is it going to get harder? Aww. When the fan cart encounters the rough patch, the acceleration changes. Find an expression for the new acceleration in terms of f, m, theta, and mu. All right. Well, I'm pretty sure in the x direction, the only real change is that now I've got friction, correct? So, I mean, I could go back to my little picture and draw an arrow here to make everybody feel better, but it's still just going to be f cosine theta minus friction equals ma. I'll put a little n there for the new acceleration. All right, it's different now. It might be slowing down, might be speeding up, I don't know. But because I have friction, I'm going to need normal force. And normal force minus f sine theta minus mg equals 0. Right, those are the forces in the y direction. That look good to you guys? This is kinetic friction. So the kinetic friction is going to be mu times the normal force, which is f sine theta plus mg. Well, I don't know why that equals 0. Ignore that. I just solved this for n and plugged it into friction times the normal force. Are those all reasonable things? I'm looking at like 2 students who are writing so fast now, they clearly had nothing like this in their practice test. I'm not going to say who they are. Oops, I found a third one. Awesome. Oh. I'm just going to substitute. So f cos theta minus mu f sine theta plus mg equals ma nu. And so now just divide by m. Is that it? Okie doke. Done. Yay. I'm so excited. Oh, wait. What condition must be met for the fan block to be slowing down? Well, everything on top. What condition must be met for the fan block to be slowing down? This has to be negative. So f cosine theta minus mu f sine theta plus mg has to be less than 0. That's the condition. Now, that's enough here. If they asked, what does theta have to be for that? Well, you might have to do some work. Or what size force would make that happen? Well, you might have to solve for F then. Or what value of mu would make that happen? Well, you'd have to solve for mu then. They didn't ask that, but those would be the things you would do next. But we just need the top to be negative. That's slowing down.